All right, hello everyone, and welcome to Back to Basics Concurrency. My name is Arthur O'Dwyer. I also do C++ training. If you have new hires who need training or want to brush up on C++ 11 or 17 or 20 or anything like that, give me an email. It's right there on the slide. And I'm also the chair of the Back to Basics track at CppCon. So let me know how you like the Back to Basics track this year. Without further ado, let's get started with concurrency. So here's all the stuff we're going to be talking about today. We're going to talk about data races. We're going to talk about mutex and unique lock, condition variable, once flag, new primitives that have been introduced in 17 and 20, a couple of idioms that might be useful to you in writing one-off concurrency code, such as the blue-green pattern, and maybe if we have time, we have some bonus slides. This presentation is geared toward people who are just getting into concurrency. They're like, what is it? What is a mutex? How do I use that? If you are working in a domain where you have a lot of threads, you're talking about green threads, you're talking about fibers, you're talking about, send, receive, and that kind of stuff. ASIO, this is not the talk for you. You're going to need a different talk. You're going to need a bigger boat. But this is the little boat for the Back to Basics track. So what is concurrency? There are two words you're going to hear thrown around a lot in this domain, concurrency and parallelism. And a lot of people will use them as synonyms, and then there will be people who say, no, 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 these are not synonyms. They have very distinct meanings. And I'm kind of in the middle. You can go either way. But roughly, I would say that to me, concurrency is the meanings in the name from the Latin, concurrent, running together. So these are things that are happening sort of at the same time, but maybe you're just switching back and forth between them. I might say if I'm multitasking as a person, if I'm writing my slides and I write a couple slides and I go answer some email and I write some slides and I answer an email, that's concurrency. On the other hand, parallelism means literally doing two things in parallel simultaneously, literally in the same instant. For example, I might be writing my slides and also listening to music or listening to a radio show in the background. Those are two things I can do simultaneously. In extremely broad strokes, I could say that parallelism is a problem for hardware. If you have multiple CPUs, you have the capability for parallelism. Concurrency tends to be done more in software, time-sharing operating systems, multi-threading. There is some overlap. Intel's hyper-threading is basically switching back and forth concurrently between things on hardware. But fundamentally, these are the kind of things you should have in your head for an intuition about these terms. So why does C++ care at all about concurrency? Well, back in 98 in C++ 03, standard C++ did not have any concept of concurrency or of threads or threads of execution. Standard C++ single-threaded, and you would just use a platform-specific library such as pthreads, like libpthread, and you add it to your link line, and it provides some somewhat standardized functionality that you call to make threads on your operating system. The problem with that is that then the standard language couldn't really say anything meaningful about multi-threaded programs. And if everyone's going to start writing multi-threaded programs, we really don't want them all to have undefined behavior, right? If we have two threads, thread A and thread B, in a pthreads program, and one of them writes to an int and the other one tries to read from the int, will that second thread ever actually see that write? Standard C++ 98 and 03 didn't say, because they had no concept of what it meant to have thread A and thread B in the first place. So C++ 11 is going to fix that, as we'll see. Also, this impacts what kind of optimizations the compiler is allowed to perform. If my original code has an int and I originally initialize it to 0 and then set it to 1 and then sleep for a while, set it for 2, sleep for a while, set it to 3, is the compiler allowed to rewrite that to say, well, I see what you're doing here. You're setting x to 3 and you're sleeping for a total of 200 milliseconds. Can I just do that? Is that a legal optimization that will make your code smaller? I mean, it won't make it faster. It'll still take 200 milliseconds, but it'll make it smaller and better in some sense. But is that legal to do? Or do I need to have X be at 2 somehow for some sense of the word? So the C++11 answer is unambiguously, yes, you are allowed to do this optimization because no other thread can possibly be looking at X during the execution of this code. As far as any other code is concerned, this is a black box. No other thread is allowed to be looking at X while I'm modifying it, and they don't know exactly when I'm modifying it. And we're going to see how C++11 turns that idea into formal codified wording in about one slide from now. The other thing that's going on with concurrency in computer programming is that not only is the compiler allowed to rewrite your code, but the hardware itself can effectively rewrite your code and reorder accesses because of things like cache lines, right? Your L1 cache has, let's say, 64 bytes in each cache line. And if you write to a sub 0 and then a sub 100 and then a sub 1, the compiler, or sorry, the hardware is quite likely to reorder that, even if the compiler doesn't. And effectively what you're doing there is 2 writes to one cache line and 1 write to another cache line, and those will be published to other CPUs in some order that is not necessarily the order you wrote it in. So when we're designing multi-threaded programs, these are all the things that might happen under the hood, and we need to use the guarantees given to us by standard C++ to make sure we don't have to worry about these kinds of things. So in C++11, we get a memory model, is what they call it. It is a formal model of what it means to be a multi-threaded C++11 program. A C++ program consists of one or more threads of execution, and each of those threads of execution executes basically independently of the others, and they communicate via memory. But every write to a memory location in memory anywhere must, what we say, synchronize with all other reads or writes of that memory location. So if I'm writing to a particular variable or particular, star p, and someone else is at the same time reading or writing to that thing, then the program will have undefined behavior. We can establish these synchronizes with relationships using various standard library facilities such as mutex and atomic. So how do we create a thread of execution? In pthreads, you'd create a new thread by calling a third-party library function, out of libpthread. In C++11 and later, threads have been standardized, and therefore there is a standard way to create a new thread. The standard library owns this idea now that this is how you create a thread in C++, and the way you do it is to create a std_thread object. That's a library class from the thread header. The constructor argument to std_thread is a callable. Usually these days it'll be a lambda. It could be a function, but usually these days it's just a lambda that says what you want the thread to do. This is your job, thread. Your job is to execute this lambda, which will print hello from thread B. The new thread starts executing immediately. When its job is done, the thread has nothing else to do, and so we say it becomes joinable. This is kind of a confusing term, join, to mean like finish up. But think of it as a single thread of execution branches at some point, and now we have 2 threads. And then at some point, their threads sort of join back together. One thread joins the other, and now we have a single thread again. So before you destroy any std_thread object, you must call .join on it. And this call will block, if necessary, until the other thread's job is finished. Block here is a synonym for wait. So here, I make a std_thread variable called thread B, and I initialize it with this lambda. By the way, I'm taking this lambda and saying, given this lambda, make me a std_thread object, which I'm going to call thread B. So it has a job, and that job is to print hello from thread B. This immediately starts executing. There's not a way to say, put it off until later. There's no thread.start the way there is in some languages. It just starts right away. We will see soon how to deal with that. So in some order, this is going to print hello from thread A, hello from thread B, or maybe the reverse. And then thread A is going to call .join on the std_thread object thread B. This says, I, thread A, am going to block and wait here. My running is blocked now by this obstacle, which is I am waiting for thread B to be done with its job, and then I will clean it up. I will join with it, and then at some point after that, I may call the destructor of std thread. That will then at that point be safe to call. We have a question: is there advantage of having a lambda versus a function for thread start? It depends on how much stuff you have to do there. I mean, if it's something like a worker thread where you have some complicated job for the worker to do, yeah, like a while loop and something, and maybe you push that off into a function and you just say, start a thread with my job, cool. If it's something simple like this, on a slide, even in real life, I would totally use a lambda for this. It's a one-liner. Why would I make a separate named function for some one-off thing? So that's what I'd say. So that was how we create a thread. So how do we get the result of that thread that we've joined? Threads don't have explicit results. There's no way to ask a thread, hey, what was your status? Because joining with the child thread is a synchronization operation. So here I create thread B, and its job now is to print hello from thread B, and then to store 42 into result. Then in thread A, meanwhile, right, that instantly starts executing. Now in thread A, I say hello from thread A, and then I block and wait for thread B. And only once thread B is done with its job and has written to 42 into variable result, and I have joined with thread B, then I read out of result, right? The write to result happens first. Well, first the initialization of result happens, and then I create this thread. And then this thread writes 42 to result, and then this join returns, right? This join might start before the result happens, but it's going to block until this thread is done with its job. And then finally, I read the result. And so this is thread safe code because we do not have a data race here between the write to result and the read from result. They are separated by the synchronizing optimization. And we say that the read synchronizes with the write and vice versa. But here's an example of a piece of code that does have a data race. So here, this is a terrible slide code, but I'm going to create thread B, and I'm going to say that your job, thread B, is to run this loop that just repeatedly prints out and increments this counter until reaching some deadline in the future, 10 seconds from now. And meanwhile, in thread A, I'm going to be doing the same thing, incrementing the counter and printing it out. This is a data race because it could happen that thread A and thread B simultaneously try to increment counter. They both try to write to it, or one tries to write while the other is reading. Those are both data races. And a data race on a regular, any kind of variable, including int, is undefined behavior. Right? No synchronization exists between these two accesses simultaneously, and that's undefined behavior. We can fix this using the standard library type stdatomic, which is a template. So stdatomic of int makes me an atomic int. You can make a stdatomic of any trivial data type. So ints, pointers, even floats. I think you can make an atomic float. And this minor change completely fixes that physical data race that we had, because by definition, according to the standard, every access to an atomic variable implicitly synchronizes with every other access. So here I have thread A and thread B, and they're both trying to increment counter simultaneously, right, at the same time. But by definition, because it's of type stdatomic of int, each of those accesses, each of those reads and writes synchronizes with everything else that's going on in the program, or every other access to that variable that's going on in the program. So there's still what we might call a logical race or a semantic data race, where the behavior of this program is kind of unpredictable. It depends on how the threads are scheduled, what you see as output. You might consider that a bug in real life, but it is not undefined behavior according to the standard. This has perfectly well-defined behavior. Right? It never has UB. So let's talk about the way that threads start. So I said that threads always start up running immediately. There's no thread.start method. You just create a thread and boom, you've got a second thread and it's running, as far as you're concerned, right? It may actually be blocked somewhere in the operating system waiting for a CPU to become available, waiting for some resources to become available. But as far as you know, it's running right away. So what if we didn't want that? What if I wanted to create a thread and set it up and say, this will be your job, but not yet. Hang on. I have a little more setup to do on the main thread. In thread A, I'm going to print hello from A. And then I want to do something to unblock thread B. And then let thread B do its thing. And then maybe I also do something in thread A and then I join. So can we tell thread B to wait until thread A unblocks it? The answer is yes, naturally, using what the standard calls synchronization primitives. And we're going to look at the rest of this talk mostly is talking about different synchronization primitives. So first, a non-solution. This is the busy wait solution. This is what you might actually do if you hadn't attended this talk. You might think, here's what I'll do. I know that I can make an atomic bool where accesses to it don't cause undefined behavior. They all synchronize with each other. And then B will just wait until the ready flag becomes true. And it'll just do a while loop. It'll just zip around in a loop over and over and over. And meanwhile, we'll carry on in A, and eventually A will set ready to true. This is not a data race because ready is an atomic. However, this is also not what you want to do for several reasons. So the main thing that is wrong with this, that you should see every time you look at a piece of concurrent code, look for this kind of busy wait. This is a while loop that's saying, like, I'm just going to keep doing something until this condition is true. And my something is not helping us progress toward that condition, right? Thread B here never stops working. It never goes to sleep. It just keeps checking over and over and over. This is like someone's in the bathroom and you're standing outside rattling the door handle. It does not help, and it may even hurt, right? You're using resources that the other person might actually be using, you know? So on a single core system, this is a huge waste of time. So you really don't want to do that. Also, this code has undefined behavior for other reasons, which is that the read and write do not cause a data race, but the compiler can see that this condition cannot possibly change as a result of anything thread B is doing, and it might hoist it out of the loop, right? Just test once at the beginning of the loop, store that in a register, and just test that register, and it turns out, oh, well, in that case, this is either it drops through immediately or it's an infinite loop, and the compiler is allowed to generate that code. So again, even with atomics, you want to watch out for doing things that the compiler might optimize in ways you didn't expect. So there are many reasons not to do this kind of busy wait loop. What could we do instead? Here's one real solution. This is the simplest solution, not necessarily the most appropriate for production code, but I think it's decently appropriate. But I've had people tell me, "What? This is crazy." Here's how we're going to do this with std mutex. What is a std mutex? It's a mutual exclusion mechanism. So mutex, mutual exclusion. That still doesn't really tell you what it is, but at least it tells you what it does, kind of. I compare this to the key to the bathroom in the coffee shop. You know, you go to a coffee shop. Remember coffee shops? We used to go there, and there would be other people there, and yeah, those were good times. So you would go, and then eventually you'd be like, well, I need to use the restroom, and you would go up the counter, and you'd ask for the key. And you'd get the key, and you'd take it in. It'd be on some sort of spoon or something, you know, and you'd go in. And as long as Alice is holding that key, Bob can't enter the restroom, and vice versa, right? And then when you're done, you return the key, you release it, and then someone else can acquire it. That's what a mutex is, right? It has two methods called lock and unlock. The lock method acquires this unique resource, whatever it is, the key attached to the big wooden spoon. The unlock method releases and returns that key so that someone else can use it. So here's what we do. We make one key, mutex, MTX, and thread A locks it. Now thread A holds the mutex. Thread B, then, we start it running. But the very first thing it wants to do is lock that mutex. So it will now have to wait. It's now in line outside the bathroom, and it is waiting to get that key. So it's blocked there. Meanwhile, Meanwhile, so that's what that other thread B is doing. Meanwhile, in thread A, we go on, we print our hello from A, and then we release the key. We unlock the mutex. That allows thread B to wake up. At some point, it will say, oh, yes, the key is available. I will now get that. I will immediately give it back, but now I can go on and do my thing. So then we do some other stuff, and eventually we join thread B. I'm sorry, this little black bar keeps popping up at the bottom here. And then we say hello again from A. We have a couple of questions about the busy wait, whether you should put a yield or a pause inside the loop, whether maybe if you're on a multi-core system that could help with latency. Those questions are out of scope for this talk. But I think the short answer is yes, maybe. But if you're asking the question, you probably shouldn't be doing it yourself. So let's talk some more about std mutex. So that was an atypical use of std mutex, where we were using it just as a gating mechanism on thread B. A more typical use for a mutex would be to protect some data. Just again, like in the coffee shop analogy, the coffee shop bathroom key protects the facilities of the physical bathroom. Here, I have a token pool class, and it has two members, one of which is a mutex, the other of which is a vector. And the mutex protects the vector of tokens. Every access, every read, every write that we do to that vector must be done according to my class invariant that I, as the programmer, designed. I've decided that every access will be done under a lock on the mutex. This is an invariant that will be preserved, and this makes my class token pool thread safe. Two different threads can now call get token at the same time. They will both attempt to lock the mutex. One of them will succeed and then proceed, and the other one will fail and have to wait until the other one releases it, unlocks it at the end of the code. And then while we have the mutex, we are allowed to do whatever we want with tokens, as long as we get it back into some stable state, at the end, and then we unlock. Protection must be complete. If you are using a mutex to protect some resource, you must use it consistently. This is necessary for correctness. Here I have two functions, get token and num tokens available. And I say inside get token, if you're modifying the tokens array, you need to lock the mutex first. By the way, if you're wondering, is this bad code because it's not using unique lock? Yes. Wait a slide. In this function, we are modifying the tokens vector. And so we lock the mutex. In num tokens available, that is a simple access or simple getter. Just give me the size of the vector. And so the programmer thinks, you know what? That's just read the size. I don't actually need to lock the mutex for that, right? It's a read. But no, that is not correct thinking, right? If someone is calling get token at the same time that someone else is calling num tokens available, the one calling get token will hold the mutex, and they will be doing writes to the vector. And if the other thread, thread B, is reading from tokens at the same time, just read the size. That is a data race. A write plus a read gives you a data race. Two reads don't, but a read and a write, those are bad. So if you protect only your writes, and then someone else is doing unprotected reads, you have a data race. So protecting a variable with a mutex must be 100%. Protect every access, or else it's no good. The only exception for that is in things like the constructor and the destructor. Because if you're destroying the object, obviously nobody else has a handle to the object anymore because you're now destroying it, right? That would be a bug of a different class if they tried to use it while you were destroying it. So there you wouldn't need to take the mutex. But this code would be bad. So let's see how to fix this code. We also have a problem here with exception safety, right? Because there is a potential bug here. If token create or pushback throws an exception, we have a bug. They throw in the exception, we have locked the mutex, but we never call unlock because exceptions, when they're thrown, abort the execution of the function. We never call unlock. So we should look for a way here. Anytime we have a resource, we should look for a way to follow RAII principles. Every cleanup action, freeing resources, freeing heap allocated pointers, or unlocking mutexes should always be done inside a destructor. So Here's how we're going to fix that. We're going to make an RAII class. In fact, we're going to use one out of the standard library. In the standard library, in the mutex header, right next to std mutex, you will find std lockguard. That is a class template. It takes as its parameter the type of the thing you're locking, which in this case is std mutex. And in its constructor, when I construct this variable lk of type lockguard of mutex, I give it a mutex, a reference to a mutex, and it locks that mutex. In its destructor, it will unlock it automatically. Now, if pushback throws, the destructor for lockguard will run and it will unlock the mutex, and I no longer have that exception safety bug. Also, that's a one-line fix for num tokens available. I don't have to worry about where do I put the lock and the unlock. I just define at the top of my function. I have a local variable named lk of type lockguard. Here I'm using the C++17 class template argument deduction, so I don't have to write mutex if I don't want to. This is one place where, even though I normally hate CTAD, I might say maybe it's okay here. Right, so we lock the mutex, we return token size, and at the end of this function, at that closing curly brace, we destroy the lockguard, and that unlocks our mutex. So a mutex locks is a resource, just like a heap allocated T-star, where when you're done with it, you call delete, lock std mutex. When you're done with it, you call .unlock. We have a unique putter to help us manage unique ownership of heap allocations. And likewise, we just saw lockguard, but just like unique putter, we have unique lock also to help us manage unique ownership of mutex locks. And just as functions can pass or return ownership of a pointer, functions can also pass or return ownership of a mutex lock. I can write a function here. Here I've got two functions named foo. One of them takes in a unique putter, that is a heap allocated int, a handle to a heap allocated int. And if some random number, some random condition, clean it up, and then return either null or the pointer that we got in. That all works fine, right? Since C++, well, C++ 14, because we're using implicit move here. Right, this is a heap allocated resource that I can prematurely clean up if I want. I can pass it around to a function, from a function, whatever I want. Similarly, with unique lock, this is, lk here, is a unique lock on some mutex, and it knows what mutex that is. It has captured a reference to that mutex, and I can prematurely clean it up if I want, or I can just pass it back to my caller. I can pass it around from function to function. This all works fine. Std lockguard is a special case. Std lockguard is not movable at all. It can be a little bit more efficient that way. It doesn't have an empty state. It's just either you construct it, you destroy it. That's it. That's all it is. So it's a little bit more efficient. If you're compiling with optimizations, it doesn't really matter, I don't think, whether you use unique lock or lockguard. But I would tend to say, if you're not going to pass it around, use lockguard. If you are going to pass it around, you have to use unique lock in order to make it movable, like unique putter. And unique lock, just like unique putter, is of course movable, not copyable. By the way, there is also a std scoped lock in C++17. It is a new and improved lockguard. It can take multiple mutexes at once, and it internally has an algorithm, usually based on sorting their addresses, to figure out what order it should lock them in. So that if you do have something like here where I have a merge tokens from function that takes this pointer and another token pool and wants to lock both of their mutexes. So here I use a scoped lock and I pass it both mutexes. And even if I'm merging tokens from A into B and from B into A simultaneously, this will not cause a deadlock because it will internally lock the locks in the correct order. So this is a very rare thing that you would have to use scope lock to lock multiple locks, but I was kind of pleased to come up with this motivating example for it. All right. At this point, we have a question break. I'm looking at the questions that the volunteer has pasted to me here. I think we've actually done most of them. There was a question about how is std thread implemented? Does it have are there primitives backing it up that are talk-aboutable? And I think the answer is std thread does tend to be fairly complicated and does tend to end up being based essentially on pthreads. at least on POSIX systems. On Windows, of course, it's based on Windows stuff. Using std-thread instead of one of these third-party libraries not only makes your code correct C++11 and later, it also helps with portability. Is it safe to mix standard library threading with the underlying pthreads or Windows threads? In general, I think the answer in practice is yes. As far as the standard is concerned, the answer is no. That's the sort of thing where if it breaks, you don't come to the standards committee and complain. You have to go to Stack Overflow and they will tell you it doesn't work, workarounds and so on. What would I prefer between unique lock and lockguard, and why? I would prefer lockguard in the case that it is just limited to a single scope. If I needed to pass it to another function, I would have to use unique lock because that is the only one that is movable. Lockguard is immobile. If a resource is going to be written by one thread and read by another thread, are there read-write locks? Yes, and we will see them. C++ calls them shared mutexes. We will see those in a couple slides. I think that is it for now. One more. Was scope lock introduced to solve the deadlock issue? That is one of its purposes. Another one was just that the existing lockguard, I don't think, played well with CTAD or something like that. There was some reason they needed a whole new class for this instead of just expanding lockguard. But even in C++11, there is a library function, stdlock, that handles the deadlock for you. All right, what do I dislike about CTAD? We'll save that for the hallway track. All right, metaphor time. All right. Let's move on to more complicated synchronization primitives. You can see our second one. So I'm going to use this metaphor a lot. I like this. We have two people in this metaphor. We have Pat the postman. Pat is going to deliver a letter. And we have Frosty the snowman. I don't know. I found this clip art. And Frosty is waiting to receive that letter, right? Pat delivering the letter to Frosty. Think about what those two initials could stand for. Here's our algorithm, our procedure for Pat delivering a message to Frosty. Mailboxes, flags, and symbols. Frosty goes to sleep next to the mailbox. Pat puts a letter into the mailbox, raises the flag, clashes her symbols. Her symbols wake up Frosty. Frosty is asleep next to the mailbox. He's been asleep this whole time. But when he wakes up, he heard a loud noise, he wakes up. Pat is nowhere to be found. They don't communicate directly. But he sees that someone has raised the flag on the mailbox, so now he can look in the mailbox and in fact sees the letter. There are some subtleties here, by the way. Frosty is a light sleeper. Truck goes by and backfires. He might wake up, he might look, but the flag is still down on the mailbox, so he knows he can just go back to sleep. Right? There are some things like that, but this is our fundamental metaphor. And this brings us to our next synchronization primitive, which is called, another name that doesn't really mean anything, condition variable. So let's say that in our token pool class that we're building, if we have no token create, we just populate our vector of tokens at the beginning, a certain number of tokens, and we hand them out. And if someone asks us for a token and we have none, then we were going to have to block and wait until someone else returns a token, and then we can hand that one out. So here's my new token pool. I have a vector of tokens. I have a mutex still protecting tokens, and I have a condition variable. And we're going to add one new member function here, return token. And what it's going to do is someone gives us a token, and I'm going to put that token back into the token vector. So step one, I take the lock, because every access to tokens must be protected by the mutex. I modify tokens. I'm putting my message into the mailbox here. I'm raising the flag on the mailbox at the same time because the flag on the mailbox is tokens empty, basically. And then I clash my symbols. Condition variable has a method called notify1. It also has a method called notify all. Notify1 will wake up one individual who is waiting on that condition variable. Notify all will wake them all up. Again, they could wake up spuriously when a truck backfires, but we're not worrying about that at the moment. On the other side, here's Frosty's side. We have a get token function. And what it's going to do is take the lock on the mutex and look at the tokens vector. Is it empty? this is our mailbox flag. If the mailbox is empty, then we're going to go to sleep next to the mailbox. When we go to sleep, we are no longer looking at the mailbox and we drop our hold on the mutex. The mutex here controls what am I saying here? The mutex here controls access to tokens. So as long as our behavior depends on the mailbox being empty, we need to hold that mutex. So what cp.wait of lock does is it takes the lock, or sorry, it already has the lock. It will relinquish the lock and go to sleep, and it will do that atomically. There will be no little gap where someone else could steal in, grab the lock, modify tokens before we went to sleep. It will atomically drop the lock and go to sleep. Once it wakes up, it will try to reacquire the lock. It will wait until it has done so, and then it will return to us. So when it returns, we still have the lock. We dropped it while we were asleep, but now we have the lock again. And again, we can look and see if anyone has gotten the mail for us. We drop out of the loop, assuming there is some mail for us. We pop something off the back of tokens, and we return that token to our caller. So this is our condition variable. In slide 26, why isn't it a lock guard? It actually could be a lock guard. The reason that I made it a unique lock is so that I could manually unlock it here before doing the notify. In previous versions of this presentation, I would also sometimes reverse those lines and do the notify before the unlock. Semantically, it doesn't matter. For performance, people keep telling me it's a good idea to do the unlock before the notify. And so that's what I've done here. In order to manually unlock it, it needs to be a unique lock because that is the only type with an empty state, right? A lock guard holds the lock all the way until its destructor, and I wouldn't be able to manually unlock it here. I could add an extra scope of curly braces, but that would take more lines. So whenever you have this pattern of a producer and a consumer, where the consumer must wait for the producer, and this production consumption cycle happens over and over, such as in our token pool, such as a task queue, a work queue, a channel in the Go sense, then you almost certainly want to have a mutex plus a condition variable. We will see later, I'll have one slide on promise and future. We're not going to talk about them a lot in this talk. They are implemented internally in terms of mutex and CV. Promise and future would be appropriate if you just had a producer talking to one consumer and it was a one-shot deal. For something like this, where it's a loop, a task queue, a channel, you want to use a mutex and a condition variable. Of course, if you can use something like threading building blocks, Intel TBB, if you can use, for some applications, maybe you want to use ASIO type things. There's all sorts of libraries out there, especially if your program is fundamentally concerned with concurrency. Again, this presentation is geared to people who are just getting into concurrency, who maybe have a one-off task that requires, using a mutex correctly. If your program is fundamentally concerned with multi-threading, you're going to need a bigger boat. All right, so C++11 made the core language know about threads in order to explain how concurrent writes to int cause UB, but concurrent writes to atomic int don't. But C++11 did another cool thing as well with this idea of threads in the core language. In main here, I make two threads, T1 and T2, and I am saying that their job in both cases is foo. Foo is a function here, takes no parameters, and it has a static local variable of type complicated object. So T1 and T2 will arrive at this line concurrently, right? There will be no synchronization between T1 and T2 when they get here. Which one of them is going to perform the constructor of complicated object? And what is the other one doing while that's going on? In C++03, when you had a static variable like this, like a singleton, you had to do things like there's a double check locking pattern, and anyway, it's all UB because there were no threads. In C++11, it is as easy as make a static local. Right? This is a valid inline function that returns a reference to a correctly initialized singleton. Only one thread will initialize this singleton when it gets there. The first thread to arrive starts initializing the static instance, the static variable here. Any more threads that arrive will, according to the standard, block and wait until the first thread succeeds unblocking them all, or throws an exception, which means its exiting out, it's done, the object didn't get constructed, and then one of the waiters will unlock and it will try its turn. This is known as thread-safe static initialization, and this is standard since C++11. You don't need any special additional synchronization in order to make this work. It just works. So suppose you want a singleton per instance of some other object. So you can't use a static, but I have this, data member of a logger. So each logger has its own optional network connection. And I have this get connection function that the first time you call it, I want it to create a new network connection and populate the optional. But this code is clearly unsafe. It's not thread safe if two threads call getCon concurrently as the first call, because they will both look at con, they'll see it doesn't have a value yet, they will both construct a network connection, they will both try to write to con. This is a data race. How do we fix that? Well, one way to do it is protect it with a mutex. This is totally fine, and we have seen this already. Protect it with mutex. Now this code is safe, but it is perhaps, that was weird, sorry, little glitch there, but it's perhaps slower than it could be, right? Because now every time we call getCon, we have to try to lock that mutex. And if there's a lot of contention, this is going to be very slow. What we can do is we can use a new primitive in C++11 called once flag, or call once. So a once flag object is a concurrency primitive like mutex or condition variable, but it only has one method. And that method, for some reason, is implemented as a free function, not as a method on once flag. It takes the once flag as its first parameter. But this is basically, think of it as the only thing you can do with a once flag is you can call once on it. When you do that, you give it some sort of job to do. And every time this line is reached, if the once flag has not yet been done, if no one has succeeded at this task yet, we will try this task, queue waiters behind us to attempt this task if we fail. The first one to succeed at this task sets the once flag to done. And from then on, anyone who calls call once on it just says, oh, the task's already been done. I don't need to do anything else. This is more efficient. Mutex every single time. So this mimics C++11 does thread-safe static initialization, but it does it for a non-static variable, such as a member variable. This is where you would use once flag. I see a lot of people using once flag for global variables, using once flag for static variables. You don't have to do that, right? This is the intended use case for once flag. So here's a comparison of the primitives, which I believe we are running far behind, and I am going to move on quickly. Sorry. C++17 is a reader-writer lock that someone asked about in the questions. A reader-writer lock is known in C++ as a shared mutex because there are two kinds of ways that you can lock it. You can call just regular .lock and .unlock, which are called by unique lock. This gives you an exclusive lock, what we would call a writer lock, on the reader-writer lock. However, it also has functions called shared and unlock shared. And these are your read lock functions. As many threads as you want can all be sharing the same lock shared. Like you can have many threads concurrently called lock shared. They're all readers. And they all do their reading stuff. They all unlock. And then finally, a writer can get in. A single writer can get the exclusive lock and do its writing thing. So this is a reader-writer lock that we in C++ call, for some reason, shared mutex. The terminology is different, but if you're familiar with pthreads RW lock, it works the same way. In C++20, we also add semaphores. A semaphore is a bag of poker chips, very similar to our thread pool. This is now sort of built into the library. It has two methods, acquire and release. Acquire removes a chip from the bag, and if there are no chips available, it will block until there are chips available. Release returns a chip to the bag. We assume that you acquired a chip earlier. If you didn't and you just keep releasing chips and adding things until the bag overflows, that's undefined behavior. But yeah, it's basically a counter that can go up and down and up and down. And if it gets to 0, it blocks until someone else bumps it up. Chips are indistinguishable, interchangeable, and not tied to any particular thread. This is different from a mutex lock. You can't pass a mutex lock between two STID threads. The thread that has it locked is the thread that has to unlock it. That's just part of what it means to be a standard mutex. But you could use a counting semaphore as a kind of mutex whose locks could be passed between threads. You would just give it a maximum of 1. Right? Someone has the 1 token, they can pass it across to another thread, that other thread calls release. That's totally fine. This makes our token pool slightly safer to use. If you saw my CppCon 2019 talk, Back to Basics Smart Pointers, you saw me using unique putters for interesting things like OpenSSL certificates and things. Here's another example where I'm using a unique putter to say, you have a handle to a semaphore, and when you're done with this token, I want you to call release on that semaphore. Someone asks, do we ever need to use volatile? No, that was easy. Please don't use volatile for anything ever. Also, in C++20, there is another thing besides semaphore. We also now have latch. std latch is an integer counter that starts positive and counts down towards 0. And when someone reaches the latch, they will then wait at the latch until every other thread has reached the latch. That is, until the counter has gone down to 0, and then they will all unblock. This is a one-shot starting gate mechanism. Wait for everyone to arrive here. We have a counter that says how many people haven't arrived yet. Once everyone has arrived, I'll let you all go. That's a starting gate. Latch is similar to once flag or promise or future, that there's no way to reset it. It is a one-time thing. If you want another latch, destroy this one and create a new one. It's a one-time thing. If you want a reusable starting gate, what I might call a pace car mechanism, if you're familiar with auto racing, you have a barrier. STID barrier is essentially a resettable latch. So again, it has a counter. As people show up at the barrier, they block and they wait. Once the appropriate number of people have arrived, the barrier comes down and lets everyone go, and begins a new phase immediately, atomically, such that if someone comes around and starts waiting again immediately, they will block and they will wait again until everyone has come around and done one lap, and then they will all get to go and come around and do another lap, and it'll unblock and let them all go. So this is a pace car. Once everyone's caught up, unblock everyone, atomically refresh the barrier. Rob says, talking about passing semaphore tokens between threads, wouldn't you need some method to pass the tokens safely? Not sort of yes, sort of no. Let's take that one to the hallway track as well. What's the difference between blocking these threads and then letting them go versus joining them? Two things. Number one, join blocks the thread that calls join until another thread finishes. A latch, you call latch.wait from the thread that's running, right? Not the main thread, but the thread that's like going around. And it blocks that thread until some other thread gets also to that point, or also to latch wait. Latch arrive and wait. And then lets them all go. I actually have a couple of examples in the slide, so that might help. There are some subtleties to SLID barrier I'm glossing over. It's really a class template. It defines a completion function. We'll see an example of that. It has possibilities for undefined behavior if you use it wrong, so it's important to read the documentation. Here is how I might use latch to solve our thread starting problem. Remember, threads start immediately running, but what I can do is I can make a latch with the counter initially set to 2. I expect 2 threads to call arrive and wait on the latch. Here's my thread B. Its job is step 1, arrive and wait at the latch. Wait for the other thread to arrive. So that's what it's doing. It's blocked there. Now, meanwhile, in thread A, I print hello from A, and then I also arrive and wait at the same latch. Notice I'm capturing a reference this latch. So my latch here and my latch here refer to the same local variable latch. Now, both of my threads have arrived and waited at the latch, and so the latch lets them both go. Now, thread B is unblocked, and thread A is unblocked. Thread A immediately goes and joins thread B, so now it's blocked again. Meanwhile, thread B prints hello from B. and exits, that unblocks A here. So hopefully this example, and it may not even be on the screen long enough, but if you go and study the slide, hopefully this clarifies the difference between waiting on a latch and joining another thread. In fact, the main thread's going to call join anyway, so we can just do this. We can say we're just waiting on one thread, and you don't bother decrementing it, just wait. One thread is still to arrive. You wait until they come. Then here, you say you arrive, you decrement the counter, but you don't wait, right? You don't need to wait. Just decrement the counter, prove you've been here, go on. So no matter what order these two functions end up getting called in, right? There's no synchronization that says what order they're going to get called in. But thread A here is sort of leaving a note for thread B that says, yes, I got here. If you're waiting, unblock yourself. If you haven't started waiting yet, you don't even need to wait. So you could do this. Are latches copyable? No. No synchronization primitives could ever be copyable. Mutexes are not copyable. Condition variables are not copyable, right? All of the actual things, they just sit in one place in memory, and you poke at them. They're very object-oriented. They have state. You could not make a copy of a mutex. Similarly, you can't make a copy of a latch. So how does this thread know where the latch is? Because it captured a reference to it. The Lambda captured a reference to it. And could this reference dangle? Yes, theoretically, if thread A finished and destroyed the latch, but we're using synchronization to make sure that doesn't happen. We're making sure that we join thread B and it's completely done before we destroy the latch. Synchronization with std barrier looks kind of similar. Barrier, as I said, is a template which allows you to put a completion function here that says, this is the thing that I also want to, by the way, like notify someone else when the barrier comes down. Latches can't do this. Barrier can. So barrier is more general. So here's my barrier. The counter is initially 2. B is setting up. A is setting up. Then they both arrive and wait at the barrier. Once they are both waiting, the barrier comes down and it prints green flag go. And then we get B is running and A is running in some order. So here's another comparison of the new primitives in C++20. And notice that all of them have this counter involved. So I put little graphs of how does the counter go. For counting semaphore, different threads are acquiring and releasing, and it's going up and down by 1 over and over. Actually, it can go up and down by arbitrary jumps because you can pass an argument to say, I want 3 tokens right now. But counting semaphore, the counter goes up and down. With latch, the counter starts high, goes down to 0, and then boom, you're done. One shot, that's it. The barrier, counter goes down to 0, and then boom, right back up to where it started, and goes down to 0, and right back up to where it started, and it keeps doing this over and over. And supports some extra complexity, which we mostly glossed over. Now we finally get to a question break on the new features here and other things. Someone asks, if I use a shared mutex, is that slower than a simple mutex? I would assume that yes, it probably is. It's more complicated. If what you need is a simple mutex, use a simple mutex. If what you need is a reader-writer lock, use a shared mutex, right? It's based on what you need. Don't pay for what you don't need, but also don't think, oh, I don't want to pay, so why should simplest possible, I really need a reader-writer lock. How can I possibly simulate that with a mutex because it's cheap? Well, you can't. If there were a simple way to simulate it, they would just do that in the library, right? So use the library type that maps well onto the actual task you're attempting to perform. Here's one slide on promise and future. If you want more on this, I do have a talk from several years ago called Future from Scratch, which might be worth watching. It's probably a little bit dated at this point. It foreshadows a lot of things that didn't actually happen in 17 and 20. So one slide intro, how do we do this? There's a library function called std async, and what async does is spin up a new thread, do this in the thread, and then it has a return. Threads don't return things. Where does this return go? Well, it goes into something called a promise, which is not shown on this slide because that's all wrapped up inside this std async helper function. And the promise communicates with a future, which is returned immediately from std async. This is the sort of thing that in C++20, we're moving toward maybe coroutines for this kind of thing. Maybe, I'm not sure. So std async instantly returns a future. And you can go on and you can async another thing, spawn off another thread, and it's doing its own job, and you get a second future. And then finally here, where we call .get on the future, that is what blocks if it needs to, and blocks and waits and goes to sleep by the mailbox. F for future, F for frosty, the other side being promise, P for Pat for postman for promise. So F goes to sleep and waits until P sends it the data that it needs. And so this get will return 1, this get will return 2, and I'll add them together once they're both available. However, this is one slide. If this sounds like something you could use in production, please do not actually base your design decision on this slide. Please go learn about this and decide whether it's appropriate for you. The STL async also has serious caveats about performance because it creates all these threads, and that can quickly run you out of resources. You really want something like a thread pool, which does not exist in the standard library. Someone was at pub quiz last night. Thank you. Someone asks, if I have more threads that arrive at a barrier than the counter initially was, what happens? Well, once you get n of those threads at the barrier will drop and it'll go around again. And then this other thread will come in late and it will join the next group to go. And then, some more will come in, and once n-1 others have come in, the barrier goes down and they'll go around again. And at some point here, you might end up with all n-1 arriving simultaneously. This sounds like it's going to give you UB at some point. But the goal of using something like barrier is to make sure you understand all the possible things that could happen. And if one of them leads to UB, maybe you've got the design wrong, right? Is there a good way to use thread detach? I don't talk about it here. You could spin off some background job that you don't really care about what happens, or it doesn't clean up very much. That's quite common in real life, but I'm not going to talk about it here because there's not too much to say about how to make it standard nice. So protect shared data with a mutex, protect every access. If you have a producer consumer, use mutex and condition variable. Make the data, best of all though, is avoid sharing mutable data between threads. I'm already going super over time, but let me very quickly get to the blue-green pattern that I did want to promote here. This comes from DevOps. The idea is that you have a blue environment and a green environment. You are running with the blue environment in production. You spin up the green environment. You move all the traffic over. Finally, you can shut down the blue environment. So what this actually looks like in C++, as opposed to DevOps, is maybe we have some global config map here. That's a map of, let's say, I don't know, strings to strings, some expensive data structure. And everyone in the program wants to know what is the current config. So those are our clients who are trying to connect to our website where the config is published, right? The config here is the map. So everyone's trying to get at this thing. And what we're going to do is when we want to change something about the config, we're going to say, okay, well, the old config was the blue version, and I'm going to get a pointer to that. I am then going to make a copy of that whole config. This is the expensive part, but we're doing this while the old config is still available and people are still interacting with the old config. So while that's going on, in this thread that's trying to set the default host name, they're going to do all the work of copying the config. Then they're going to modify this new config. It's okay to modify it without taking a mutex lock because we are the only person yet who knows that this new config exists. So we can modify it without a mutex. Finally, we're going to use an atomic operation. C++ 20 adds atomic operations on shared putter. And so we can atomically say, if the current blue version is still what it was, no one else has swapped in a new version there, then I am going to swap in my version. We didn't talk about this verb compare exchange or compare and swap in this talk. If that is interesting to you, you're going to need a bigger boat. But that's something you can do with an atomic. You can say, I want to swap atomically that value for my value. So that's how we then publish our version. As soon as we publish it, we have to stop writing to it. The published version is read-only. And on the read side, All we need to do is load from the atomic. Now we have a shared putter. And now we're participating in reference counting on that actual heap allocated config map. And so we can go, look up things in it, whatever we want to do. And we will keep holding that reference count, and that thing we're referring to will continue to be good, at least until we are done with it and drop our reference count. So we have this read-only reference counted source of truth, and anyone who wants to change it reads it in order to copy it, and then atomically swaps out their new version for our version. So this is a pattern that is useful for one-off cases, like I have a program that uses a bunch of threads for something, and they all want to communicate with this config map, and I didn't want to put a mutex around it. What do I do? How do I make it thread safe? This might be a pattern that could be useful for you. In conclusion, we won't get to the bonus slides, but remember, data races are undefined behavior. One way to get around data races is to use a mutex to protect all the accesses. It must be all. It must be unconditional, 100%, both the reads and the writes. Thread-safe static initialization is your friend. Use static variables fearlessly, right? I mean, they're still glorified globals. They're not good in terms of program architecture. But in terms of thread safety, you don't have to do anything else. You don't have to use once flag. It's thread safe to use a static variable in C++. If you have a non-static variable that you want to initialize only once, that's when you pull out once flag. Mutex and condition variable, two great tastes that taste great together. C++20 introduces these three new counting primitives, semaphore, latch, and barrier. And finally, for the third time this talk, let me repeat, if your program is fundamentally multi-threaded, if you're going to write something that is complicated and real-world and multi-threaded in a fundamental way, please don't base design decisions on the intro stuff in this talk. Please use, look into Promise Future, look into C++20 coroutines perhaps, look into ASIO, look into TBB. And again, don't base your choice on what you saw on these slides. With that, let me take some more questions if we have time. And bonus slides, you can see when the slides are published. There will be a GitHub repo with all of the slides. And I will hang out, let's say in the hallway track floor 10, come table 1, floor 10 for questions we don't get to here. Do we have any other questions? There was a question about the coroutines. How will that change the way we use threads? I think that is probably out of scope. The short answer is I don't know. I don't know that much about coroutines, and especially, like, I know some about generators, the co-yield stuff, about how co-await is going to end up working with thread pools and executors and other things that we don't have. That is even further out of my area of expertise. Someone asks, would semaphores be the preferred synchronization mechanism going forward for producer-consumer? Rather than a mutex condition variable, could I use a semaphore? Yes, I think I see how that would work. Would it be preferred? It might be lighter weight. I might suspect that it would be lighter weight. I certainly don't know in practice. I have no benchmarks or anything. But it's plausible to say that if you had producer-consumer, you binary semaphore. There is a type def in the semaphore header for binary semaphore that just has a max of 1 and just goes up and down and up and down. Is there data for me? Yes, there is. Is there data for me? Yes, there is. So yes, that might be appropriate if you're in 20. Will the bonus slides be available? Yes, they will. All right. I think that is it. Thank you all for coming. Enjoy the Back to Basics track. Give me feedback. I also do training. Send me email. Thank you very much. I've been Arthur Redwire.